Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 77. Now in the previous lecture, I was talking to you about the nuclear chemistry of meteorites and how that could be helpful to determine the age of a meteorite sample, and from that how we could get the age of the solar system itself. We shall elaborate upon that aspect in today's lecture. Now we saw that the key equation describing the nuclear chemistry was, especially the transformation we were interested in, is the 238 uranium to, by a series of transformations, to 206 lead. Note, this is not just one step. So the U238, right? U238 is formed via nucleosynthesis especially involving fusion of nuclei, of smaller nuclei. So this was a point I didn't tell you in the last lecture. So the U238, that is the uranium-238 in the meteorites. So, because it's very natural to ask this question, of course, you know, we are using U238 to eventually determine the age of the meteorite. But how do you know there is U238? Well, that was determined using mass spectrometry. And the next question is, how was it formed? Because you know, when we studied the formation of the meteorites, etc., in the, first 4 or 5 lectures, we did not discuss how some element as heavy as U238 would be formed, right? Well, now I'm telling you that there are, of course, lots of details. I'm skipping a lot of those details, but in general, your uranium-238 is formed via nucleosynthesis by fusion of smaller elements, right? Right when the meteorite is formed. Okay, for example, you know, we talk about this molecular cloud, right? Molecular cloud, and then solid rocky materials coming away from the molecular cloud and accreting as like rocks. So in that process, uranium-238 also got incorporated in the meteorite. Okay, please note this. All right. So then, having understood that U238 got incorporated in the meteorite during their formation stage, that is eventually getting converted to lead. What was the mathematical equation describing this overall decay process? The math of the nuclear this is nuclear chemistry, okay, was NT is given by N naught e to the power minus KT. Now this NT can be obtained by, you know, from the amount of data, the amount of lead that is formed from so you can understand that, oh, if this much of 206 lead is formed, this had to be come from this much of U238, and your N naught is obtained from the half-life of U238. All right. So, well, I remember from the last lecture that the half-life time was given by ln k. Sorry, ln if I'm correct, ln 2 by k. Okay, and your K itself obtained from, you can measure the radioactivity and plotting the number present at any time versus T. So this is how you overall see. This is the fundamental equation. This equation can be modified to actually account for the exact number of atoms of lead present, the exact number of atoms of uranium present, etc., etc. But broadly, this is the idea. Okay, there are going to be more details. That is, this equation could be further modified, but let us not go into these details in this particular lecture. Okay, so I'll tell you that broadly, this is the idea. All right. So broadly, this is the idea, and so Nt you get from the amount of lead that is present, your N0 that you get from the half-life of uranium, and the half-life itself you get from the decay constant, and the decay constant you get by plotting Nt versus T, right? By measuring the radioactivity. You have like various counters that measure radioactivity. Now, why do I say this? Recall that in this class, okay, in this course especially, whenever I've been giving you an equation, note that in any equation, given one equation, we can only solve for one unknown, right? So we must always know what are the knowns and what is the unknown. So overall, what is the variable that we are solving for in this equation? We are solving for T. So when we solve for T, we get to know how old the sample is. I also tell you once again, this equation is further modified, to include the amount of lead present at any given time, and then the amount of U-238 that is unreacted and present, and all of those things. But eventually, they all can be brought back to this form, and that's why I've given this specific form. Please note this. Okay, and yeah, and remember that in one equation there is always one known. So in this course, throughout, you may also go back to whenever I've introduced any equation, I've always told you, that this is the unknown and these are the known parameters. That is, we get this by calculating, we get this by experiments, and we calculate one unknown. So this is an important lesson. Never forget that. I think, to the best of my knowledge, whenever I have introduced an equation in this course, I've always clearly told what the unknown is and what is the known thing. Okay, so as you are in your undergraduate program, and as you aspire to do especially research, you should be very clear about what is unknown and what is known. I'll just make this as a general note. Okay, general note to measure something. Okay, to measure some quantity, it is not sufficient if you know what equation is to be used. Okay, so what I've written is, to measure some quantity, it is not sufficient if you know what equation is to be used. Okay, you must have a clear idea. You need a clear idea of what are known. For example, here the Nt is known, N0 is known, E is of course your irrational number, and K is also calculated, but T is what you determine. Okay, so you must have an idea of what all are known and what is to be computed, because otherwise it's very easy to fall for this lack of detail game, where you just tell that, oh, I calculate some parameter using an equation, but how do you use the equation? How do you calculate the other terms? That's always important. Keep it in mind. Okay, all right. So on that note, we now understand that we can calculate the age of a meteorite. So by computing T overall, by computing, we can get age of a meteorite. And why is carbon dating not useful here? I think I mentioned this in the previous lecture too. With carbon dating, we can estimate the age of samples which are roughly 50,000, 60,000 old. But the age of meteorites are much older than that. Example, some of the oldest meteorites. Okay, a meteorite called as Allen. If I'm correct, it was its age was determined way back, some 30, 40 years ago. It's a meteorite whose age was measured to be, can you guess the number? It's approximately 4.56 into 10 to the power 9 years. In other words, we are talking about roughly, 4.5 billion years. Right? We're talking about 4.5 billion years. This is how old the meteorites can be. All right, please make this note. So, the nuclear chemistry of meteorites can give us information about the age of the meteorite sample itself. Okay. Now, two natural questions arise. One is that. So, two questions which arise at this stage. The first question is A. What if my meteorite does not contain U-238 at all? Right? It's a fair point. Why should U-238 always be present in the meteorite sample? Well, in that case, the answer is you can still this broad idea of nuclear chemistry and this concept of radiometric dating. That's what the whole idea is called. Okay, you can still use it for whatever metal is present, and invariably, be it the stony chondrites or achondrites or the irons, right? There is always going to be some metal present. Noting that in various proportions. We're not caring about the exact composition. Okay, so even if U-238 is not present, we can always use nuclear chemistry of other metals. One prominent example is you can use the nuclear chemistry of 27 aluminum, which undergoes decomposition to 26 magnesium, which is stable, to also determine the age of the meteorites. Okay. Now, of course, different meteorite samples can lead to different ages. So this is apparently from some of the oldest meteorites, and they do incorporate U-238. Okay. Now, so this was the first question. The next logical question is, how do we know that all the 206 lead is formed only from the 238 uranium? What if 206 lead was already incorporated into the meteorite? Correct? So in that case, the whole analysis would be null and void, right? The answer is this is where which do not contain any lead to begin with, right? And they strongly, extrude away any lead formed otherwise. So meteorites called zircons are extremely useful. I mean, meteorites not called, but containing. So zircon is a class of mineral. You can look up the exact formula by just Googling or doing an internet search. I'll leave that to you. But the idea is there are some materials called zircons which with 100% assurance do not have any lead to begin with. So therefore, you can analyze the meteorites called zircons, right? So these meteorites called zircons are useful. So they do not contain any 206 to begin with. And so therefore, whatever lead is going to be noticed in it is going to be coming from the U-238 uranium. And hence, following the nuclear chemistry, you can estimate the age of the meteorite appropriately. Are we clear? Okay, so I'll write it down. So this is where meteorites called zircons are useful. They do not contain any 206 to begin with, which implies the 238 uranium, via a chain of nuclear reactions giving 206 lead can be used. Used for what? To get the age of the meteorite with precision. Are we good? Okay. So these are two prominent questions which are very natural when we discuss the concept of nuclear chemistry to determine the age of a meteorite. Now, following this, recall from our earlier lecture, that was yesterday, that I told you that the formation of a meteorite is also closely associated with estimating the age of the solar system. I made this statement yesterday, but I did not substantiate it. You may be wondering, well, why should that be true? Why is it that the age of a meteorite, be connected with the age of the solar system? Let's address that issue now. And for that, notice this. What is the connection between age of meteorites and the age of the solar system? Well, the answer is, so this is also a very fair question, right? Why should the age of any meteorite be connected with the age of the solar system? The answer is that, see, many of these meteorites were formed in the initial stages of the formation of the solar system. Okay, so many meteorites which contain U-238, such as, for example, the zircons, the many chondrite especially. So I'm sure you understand what chondrite means from, I think, the lecture, the previous lecture, or lecture 75, where I was discussing about the broad classification of the meteorites. Okay, so many chondrite meteorites were formed right during the formation of the solar system. Well, how do I know this? Did I go and see this? Of course not. Indirect evidence for this assertion, okay, comes from the idea that, so evidence for this statement that I have given right here, which is that the chondrite meteorites were formed right during the formation of the solar system. Evidence for this statement right here comes from the fact that when you measure the composition of the non-volatile and refractory substances in the atmosphere of the sun. Okay, so when you measure the composition of the non-volatile and refractory substances in the sun's atmosphere, how do you do this? Well, you do this by spectroscopy, okay, because you cannot, of course, go anywhere close to the sun, right? No spacecraft or no orbiter or anything, okay. So, but you do get light. So therefore, using spectroscopy, and you get the intensities, and using approximations of local thermal equilibrium, etc., you can get this data. Remember, we also have some equations such as the Saha equation, etc., which will help in determining the composition of the sun's atmosphere. So you can measure this and compare with the composition of the chondrites. Now, what this tells, I mean, after doing this, you find that they are remarkably identical. I'm not quantifying it, I'm just giving a qualified statement, and it was found to be remarkably identical within some error bar, of course. Okay, So this implies that the conduit materials, since they've been formed, they have not changed at all. Point number one. And also that if the age of the meteorite is going to be something, right? The age of the solar system is also going to be the same. Are we clear? Which implies overall that the meteorite's age can be associated with the age of the solar system itself. Are we clear? So now therefore, what is the age of the oldest meteorite we just saw? It is roughly 4.5 into 10 to the power 9 years, or 4.5 billion years, right? So therefore, the age of the solar system is also known. In fact, scientists are pretty confident in this thing, okay, right? That the age of the solar system is approximately 4.5 billion years, right? So what I've written here is 4.5 billion years. Around 4.5 billion years is the age of the solar system. And how do we get this? We get this from the present that nature has gifted, in the form of meteorites. And we use the basics of physics and chemistry to measure the age of meteorites. And because the compositions are found to be identical, this is a strong evidence. Of course, no one actually went and saw this. That's always there. But this is very strong evidence that from the age of the meteorite, we can get the age of the solar system itself. Are we good? Okay. So this is one more use of the nuclear chemistry of meteorite. And we now understood the statement I made in the previous lecture as to how exactly the age of the solar system could also be determined by the nuclear chemistry of the meteorite. There is one last aspect of meteorites that I want to address in this lecture. It is that, see, the idea is that meteorites also explain how the Earth was born. Isn't it fascinating? So from the meteorites, we get an idea about the age of our solar system. Okay, but meteorites also present us with the knowledge of how the Earth was born. When I say born, okay, it's within quote. We're not talking about the way mammals are born or any plant is raising. Okay, in general, how the structure of Earth that we know, especially the primordial or primitive Earth, how did it come to be? That's what I mean by born. Okay, all right. Now there were actually two strong contenders, two strong theories for how the Earth was born and how meteorites explain it. One of them is called, so two proposals based on experimental evidence, okay, is what is called as the cold accretion theory, and the other is what is called as the hot accretion theory. Now, as part of the cold accretion theory, we will look at both. I'll write it down here. I'll just call this CA and I'll just call this HA for the sake of brevity and ease of writing. So as part of the cold accretion theory, now see, how do all these meteorites get formed in the first place? They were all asteroids at some stage, right? Now they were all asteroids at some stage, and the asteroids are formed as the rocky substances as part of the giant molecular cloud. Okay, in the case of the solar system, the molecular cloud from which the rocky substances separate. Go back to lectures 4 and 5 again, please, okay, to understand how the meteorites are formed, the asteroids are formed. So, as the rocky substances eventually forming the meteorites separate out, okay, from the solar nebula. I mean, don't worry about what the solar nebula is. It is just a fancy word for the molecular cloud surrounding the formation of the sun as a star, okay, which is just a molecular cloud. So the solar nebula is nothing but the molecular cloud of sun in its primitive stage, in its formation stage. Okay, so as the rocky substances formed out, they were initially very cold. I'll continue here. They were very cold. Well, how cold is cold? In this case, we're talking about approximately less than 100 Kelvin. Now, they all got deposited on Earth, right? And followed by, all these rocky substances getting accrued. Okay, what happened is, it is hypothesized that they all, get attached to Earth. Okay, they all become meteorites, and then they fall on Earth, which is by now some kind of a large surface. Okay, right? So they fall on Earth. See, when I say they fall on Earth, they constitute Earth itself. Okay, I must say that because we are talking about the formation of Earth. So instead of using they fall on Earth, they come together. That's a better phrase. Okay, so they come together and they're still very cold. But then notice that these rocky substances also contain, material which is active for nuclear decay. So they come together and have material which is active with respect to nuclear decay. For example, uranium-238, you're talking about 27 aluminum, etc., etc. Now, what happens is, as these elements, these nuclear active isotopes, okay, as they decay, they warm up this rocky surface. Okay, so this is point number 1, and this is point number 2, and point number 3. Nuclear decay of these, I'll just call this ND, nuclear decay. ND warms up the rock, T. All right, so the rocky surface is getting warmed up by the nuclear decay. All right, so once the rocky surface is getting warmed up, what happens next is it warms it up so high that the temperature roughly becomes as high as 1500 Kelvin. All right, so the temperature here is as high as 1500 Kelvin. And so what happens next, we'll see in the next lecture. Okay, so what did we see in this lecture? I'll give you a brief summary. We were discussing about terms involved in the equation describing the math of the nuclear decay of the isotopes. And then I told you how the age of a meteorite could be connected with the age of a solar system. And at last, we started discussing about how meteorites also explain the formation of the Earth itself. There are two hypotheses. One is called as the cold accretion theory and the hot accretion theory. We are somewhere in the middle of the cold accretion theory, and we shall continue with this in the next lecture. Thanks a lot.